were like, oh yeah, we're more like it's just so scary, like between the word and it. Where it's like, I'll be strong with it, yeah. Well, it's just like a hooray song.
All right, for those that are online, can you hear okay and see the screen? Blurry, but. Okay, great, thanks. All right, questions about anything up to date? You guys good? Okay, so summary is that we have, that's a little blurry. Okay, so we moved to RLC. So first we did RL, then RC, and now we're moving to RLC. And so with RLC, you can determine what the form is between that initial and final. And then from there, you can say, well, if it's overdamped, it's going to follow this equation. If it's critically damped, it's going to follow this equation. And underdamped, it will follow this equation. And then you have the unknowns in those equations. So to be able to solve for those, you need to know series or parallel. So that's the first thing, is to determine if it's in series and parallel. What stage do we look for in series or parallel?
Final.
The final stage. So we need to know the final stage. And then determine from there the connections between the inductor and the capacitor to determine, are they looking like they're in parallel to each other or in series in that final circuit. So key is that final circuit to determine that. From there, you're going to find alpha and omega naught based on the equations for series or parallel. So if it's series, you're going to use R, which is RTH. That's going to be the RTH between the terminals of A and B of the elements. And again, RTH will be what state for the circuit?
Final.
Final, correct. Again, final.
Is there anything that we look at for the initial besides just like VC of 0?
Just the initial values, correct. So all the other ones are always going to be in the final state. And then for parallel, it will be 1 over 2 RTHC. And then you're going to find, to determine the initial values, which would be like VC of 0 or IC of 0, and then the final value, VC of infinity or IL of infinity. And then some of these for overdamped, you need to know the roots. Remember those characteristic roots, S1 and S2. And then for underdamped, you're going to need this other one called the omega naught, or omega D, sorry, the damping frequency. And so those would just be from the equations themselves. Once you get all those variables, then you can just plug into the general form of whichever characteristic it's in. Does that make sense? Yes?
Can we get a reminder on what S1 and S2 are?
So those are the characteristic roots of the, let me go back to, remember where they were under. 1, 2, here. So when we solved the RLC equations, and we turned them into that second order differential equations, And then from there, if you substitute in, like, the differential is actually a variable, like x squared, it looks like a polynomial. You can solve those then for that polynomial form just using the quadratic solution. From there, you get, you know, the x is equal to minus b plus minus b squared minus 4ac over 2a. Based on that b squared minus 4ac value, if it's going to be less than 0, it's going to be imaginary, right? And so you're going to get some oscillations. And so that gives you the characteristic. So that can be, sorry, let me back up. Square root of b squared minus 4ac, the value of b squared minus 4ac is called that characteristic equation. So it can either be equal to 0, it can be greater than 0, or it can be less than 0. So those are the three, do you remember that from math? Those are the three kind of characteristics it can take. So those are going to, in our case, tell us, you know, is it overdamped, underdamped, or critically damped? And so we substitute in B, A, and C with alpha and omega naught. And then the roots of the whole thing, which is minus b plus or minus square root of b squared minus 4ac over 2a, those we consider the roots of the system. And so S1 and S2 are going to be the roots of that solution right there. And so let me give you an example. Like, say S plus 4, S plus 2 equals 0. So say we end up with, okay, this x ends up being, or S in this case, ends up being a minus 4 and a minus 2. Those are considered the roots of the system. When we plot this, we actually plot it in the imaginary domain. And that value of minus 4 and the value of minus 2 are over here. And depending on our equation, if they're in the top, they're called zeros, and if they're in the bottom, they're called poles. And we'll get into this in more detail, but just to kind of expose you, you would actually graph this like this, and those two locations would be minus 2 and minus 4. And those would be considered the roots of the equation. If there's imaginary in there, then they're going to be kind of up or down, depending on where they are in there. They're not going to be on the real plane. And so those are called the roots of the system. So S1 and S2 in this case would be minus 4 and minus 2. Okay? Does that answer your question? Probably a little bit more detail than you wanted, but just to introduce you to what we'll get into next. That's where the next part of this will go after RLC. But you do want to understand that those are just like, okay, they're a solution to that second order differential equation is what that S1 and S2 is from. Okay? Any other questions? Okay, you guys ready to do some more problems? Okay. Okay. So 6.24. I don't know why. There it goes. Okay. So in this one, you want to determine IC of t. And so, and we're going to plot it this time. You won't have to plot it. I'll show you the graph of it just so you can kind of see what it looks like. But I do want you to solve this. So why don't you guys work in small groups? I did start this last time, so if you have those notes, you can use those to start with. If not, go ahead and restart this from scratch and work on trying to solve this. All right, there's quite a few of you online today. If you want to just go ahead and you can annotate on this screen, or you can just voice and ask people's opinions, trying to solve this. So try and solve it on your own, and then talk to each other on the solution. That's to find RTH, yes. But first you have to identify is it in series or parallel. That would be parallel. Yes, that will be this one. Find RTH, and then that will be to find alpha and omega naught. You first need to determine if it's series.
Press the sources.
So, in the final position, this will be open.
I don't think it really matters. Because
Or
you're only
you would
considering
this one.
one
Or you can if you suppress the current sources zero.
I don't think it's parallel, it's still.
So you're, so you're considering it when it's at the final time, right? So the switch is open.
Yeah, that would be series.
Okay.
For what?
You find series and parallel at the final point. So the switch is open.
Yeah.
Yeah.
Uh-huh.
Okay, and then we're only looking at the relationship between the inductor and the capacitor. So
Right.
like the middle line.
I know.
Yeah. So
But
they're on the same
if
frame.
if the current source becomes a wire,
The current source doesn't become wide. The current source becomes an open circuit. And you suppress the current.
So sorry about that. L is 0.05 Henry. You are gonna need that. There you go.
Even if it does become a wire, though, that doesn't change where the inductor and the capacitor are.
if it became a wire, it would be in parallel.
No, but the,
Yes.
the capacitor and the inductor don't move, even if you change it to a wire.
But they would.
Which is your argument?
It's in relation to each other, not the rest
So
of
it would be in parallel if it was closed, like if the switch was
Yeah, if it's
closed.
closed, of course. Yes.
It would be in parallel, but with it open, that's why you have to know, like, look at it in the final.
I agree with you. I think it's accurate.
Did you guys get series parallel?
Series.
So it will be easier to rearrange the resistors when you find RTH. But the first step of just finding series or parallel is to redraw it with the switch open, so the final state for the switch.
Series, right?
So then you hopefully can see the third series. Did you see the third series?
Oh, yeah. So John, you can remember current source.
I try not to memorize that, so voltage equals 0. You think about like, well, if I measure this more, if I something is really fast, I have the same spot. So that's where
Because
it's
when you
wire.
plug it into the
And then you can either remember
if you have that
where it is opposite that,
Okay.
or if you could be like, well, currently 0,
Perfect six.
that's like a
So
floating
that's the
wire,
reason that they
which
did
means
round
open,
it.
because they're floating.
Oh.
Just so you get it.
Right, okay.
So that's
Which is kind of silly.
Okay.
not trying to memorize them, just thinking about.
Just think about it.
Well, what does it mean when I is 0? That means there's nothing in between.
Okay.
Which is 0. So that's more just, what do you like to visually see? So you can. Oh, I see. Yes, you can do that when it's in the open, the open spot, because then it solves. Yes. And then having the inductor next to the capacitor makes it easier to see. So when you do that, the easiest thing is to like totally ignore the other purposes of it and just look at this one little one, which then it will be just one node on the top. And you know voltage from there, you have minus 1 milliampere and the A or PX, whatever you're trying to teach.
They normally think math. Okay, they normally teach you.
Yes, I
Yes,
know.
because they know, I have to think about it in strings.
Yes.
Every single time.
And it makes sense.
It makes sense, yeah. But like here, it's like.
Go crazy, so it's over that slow.
Okay, so first off, which one, series or parallel?
Series.
Okay, should have found it's in series, which is correct. And then, just so I don't have to copy all of them, did you find which one?
No, because I did the ones below.
Ah, okay. Okay, so alpha is series is going to be this equation. And then omega naught is going to be this one. That's what you needed? Okay, so series. And then, right one. Anybody find yet? Okay. So this would be your equations for overdamped, which it is. So make sure you do find that it's overdamped, and then you're also going to need S1 and S2 for this one. So those would be your set of equations. Yes.
Is R RTH
Uh-huh. Yep.
with suppressed sources and everything?
So for RTH, if we only have independent sources, which we're only looking at independent sources in this class, you'll remove those independent sources. So suppress them or set them equal to 0. All right, so for that final circuit, what is the trick to find RTH? Correct. So reordering those so that the L and the C are right next to each other. So once you redraw them, try and get, okay, redraw the final one. So once you redraw this, you can see like, well, those two elements, the L and the C, that's a little confusing. So if I redraw them, this I hopefully can see that is totally floating. So I can ignore that one. My L is here and my C is here. So to get RTH, what happens with the current source? Okay, it will go to an open. Remember, I equals 0 looks like a floating wire. So that's how you can kind of remember that it's open, right? Floating wire means no current flowing in it. So from here, if I move over, so now I know like, okay, they're in series. So in series, I can move elements in my branch around. So if these look the same, sorry. That looks better. So if I move these around, then it is easier to see that now when I remove my L and my C, and replace them with like an A and a B, it's very easy to see where the pathway is. Otherwise, it looks a little confusing. So RTH is
0.62.
0.62 is all. Okay. Move out of the way.
Might want to get used to using it on your iPad. Is it an iPad?
Like Desmos on here. I have my calculators in my house, but
Oh, okay. Yeah, I don't have a great phone app on it. I use Desmos on this. There, you can download Desmos on your phone.
Desmos is definitely the best.
Whatever you feel like you're gonna use during the exams, just want to get used to it.
Great.
You know where you're gonna.
Then you go to the equations, right? Or you go find the initial current.
Right before that, you need to calculate.
Oh.
So that'll be series and parallel, and then those two equations first. And then go to the initial. Nice. Do you know where to go after you find series and parallel? Okay. So did you find alpha and omega?
Alpha's in like meters per second or something. Right?
And then you see how to look at that.
I would look at that. I recently found the initial voltage of 0.2.
I'm just looking at equations down right now.
And then goes to the final.
But, good.
There you go. Okay, so you know how to find alpha and omega?
I did get those. It's a current source, unless you choose to. But you can do it with a current source.
So for everyone, remember when you're finding IC of 0, you need to do that extra step by replacing the capacitor with the voltage source and the inductor with the current source of what you find in the initial circuit. That's how you'll find IC of 0. In this case, it's not going to be 0.
So you use the, that's the volts, and then the initial current.
Okay, so you got VC.
Is
total amps times the 0.1 amps, right, 0.4 is 0.2.
It will be, say that again. How do you balance? So it's gonna be. So in the initial zero, in zero minus this, switch is still closed. And so this circuit will not be valid. You wanna redraw that circuit with the switch. So this will be open, and this will be a wire. And then you wanna find the current.
I might be wrong, so not trying to move on, so no current, but one this side here.
I see the direction.
So all of your voltages are two right here, so we could leave the voltage.
So you can calculate it by just putting the voltage
Current times by, so it's 0.4, not 4.
yes, probably that, and then V over the
Okay,
0.1.
when is that, when are so with the, is it?
No, because in time,
because
it's 4,
I can
it's
see
closed.
because I think we have to do the limits of voltage sources. And that's the.
So this is like a 0 minus, which on this we get exactly 0.
I think we have to do as a limit.
Which is it,
And I think the zero minus tells us the capacity.
is it capacitor's charge?
And then the.
So are we just saying that that's not? The final current will be 0. I see infinity will be 0, but VC eventually is.
I think because there's
Right,
and so
and then
because
you're
they
after a long
want
time,
to
it's gonna go to wire.
Yeah, right now, this is replace this with the voltage.
I guess the other part is,
so there's
is
going
it
to be
power source is always connected.
So I see.
so then once we go this way and this is no longer this part's no longer there, it's going to force current.
So that will be your initial here, and then when it opens.
So I think we have to use
And that may push the current.
so I did it on order, so this is 0 minus and this is 0 plus, this is infinity.
So it's always
So
0 plus.
I took out the inductor because I wasn't sure what was supposed to get there.
Because that's right after.
But I think it's an
So
active.
you're always trying to find it from that point to.
Because the current through the
So
inductor
that
right
0
here,
plus is always.
like before the switch is open and after the switch is open, it has to be the same.
No, it's always the same, but in the RL and RC, we just found, we pretty much just found AC or I. But if we wanted to like any other kind of short variable, we'd have to do it.
Right.
You use 0 minus to get 0 plus. Because you know it's a voltage and a current.
Our IC is defined.
So you're really just using that to get the initial value.
Our IC is defined as what? Our IC is. Yeah. That's what we're.
How does it?
No, because in the final one, you just now becomes open.
After it charges, it doesn't have to be so after a long time, it's gonna be just a wire that's gonna have the same
And then the resistance jump one.
That's why it's easier to redraw them. Redraw it each time. Sorry, what are your questions? Uh-huh. No. So you wanna redraw the circuit, this is gonna be open. And then this will be wired.
Okay, so we have the voltage.
The different.
x equals 0 minus, because that's what we're looking at, right? So before the switches, right, it's this one and this one. And those are the only two rows that choose like this current.
I mean, you'll have the current.
Give me a second. Okay, so then, so there's 2 milliamps going through this wire and 2 milliamps going through there. Yeah, there. Okay, so then we know that the inductors act, it has to still have 2 milliamps going over it. Okay, so then there's a 2 milliamps going this way. So there's 2 milliamps going over
So
there.
this is your circuit, that's your minus, right?
Okay.
So you wanna find the current going in that wire. You know what that will do, or how you do it. Yeah, because that's really important.
If you find the Vx over, the hypothesis.
So you would just do, you already found this one, right?
Right.
So that was 0.29
We'll
volts.
do it over the point back.
So there's no current there, all the current's going there.
Okay.
So I see 0, this current is 0, but IL is the voltage over that is. Right, because this current all goes.
And then, so,
So then this becomes that 2 milliamps.
oh, okay.
So as you replace it, whatever value you found
And
there.
then do it keep the formula?
Yeah, but it's- you have a current source, that should be here. Only for RTH does it not go in. And then, so this is not the same. So, there's, you know, the inductor is here, and then you have. Oh, sorry. Okay, never mind, yeah, you're right. Okay. Number 2, yeah. Okay. And then. So now the VC infinity, the VC infinity is gonna be, what's the current in here? This is a floating wire, right? No, floating wire, what's the current in a floating wire? If I have just a floating wire out there, 0, yep. So this is 0 current, right, 0. And then you want the voltage, which is here, which is across this 1.1. So before milli. That's the point.
Okay. Is this right,
So when I'm
how I
doing
did everything here? Because this doesn't make sense, because here I say it's 0, so there's the voltage drop across this resistor.
You guys got it.
But here I say it's 2 milliamps.
So if you're looking at this, you know, 2 milliamps comes in,
And then there's a
then you have whatever this voltage, 0.1, and then this voltage minus it would be simulated.
I'm trying to, and I see.
So then you would have that equation. So you don't really need this information, you already know what you're
Right.
So it says.
It's like a measurement across
So what I
this.
did is, you said this is.
But is it gonna be 2 milliamps? Is that like right? Is IC 0
Series,
2 milliamps?
right in parallel. Yeah, so then you have
Just do the same
negative
thing
10.
with
It's going
Because if I define IC 0 as going there, I guess I should
So then
define
you
it
have
as that
negative
one.
4 times 10 to the negative 3.
This current is 0.
Plus mu of x over 5.
So saying that this is IC 0 is wrong.
I got v of x is 0.02. And then
There is
it would just be
Since
v
this
over
is
RT.
this is IC 0 on this. And then how do I find
So
VC
v
0?
of x, which is 1.02.
Okay,
And
so-
then voltage.
Yeah, you would do the voltage.
So then 0.025 is 152 to get IC. So I got
After very long time. I kind of knew it, yeah. There's no voltage drop.
this one.
Right, whatever that is, so that's what that would be.
Way better than.
zero
Twice
and
by
voltage at that node?
Yes.
So just voltage across this whole thing?
Mhm.
Okay, cool. So you found, really have to break this along this route.
It was
Sure. But the number should change, right?
Oh,
Or the event should change, so it shouldn't matter.
So,
I don't think we care about
like,
how much goes down this week.
okay, so in this one, this should be open.
Goes down.
This,
Because I guess it's a little harder than it should be, right? Because right after it switches
Right,
open.
so it's
So
the-
this is the circuit that you're solving.
Oh, this is for the initial.
so it's actually just two nodes.
So initial would be till
I
zero.
don't remember reading that, right? So, yeah.
It'd be great to
That's
make
the
sure
circuit.
the circuit equates that.
I see.
Like,
Zero.
zero, zero,
Yeah.
that's set.
Yeah, so-
Okay, yeah, okay, awesome, thank you.
Yeah.
Right, so it's really worth it.
Okay, really.
okay.
Right before?
So I think some of you have figured out that it becomes a little harder to figure out what those initial currents are, correct?
Yeah.
Initial current and that initial voltage. So the key here is that you know that the voltage across the capacitor and the current across the conductor stay the same before the switch and after the switch. Those values are used to solve for any of the other initial currents or voltages in the circuit. So in this case, at 0 minus, the switch is closed, the inductor becomes a wire, and the capacitor stays an open. So I need to know this value and this value, and those are the two, only those two stay the same. So once I get that, I then redraw the circuit with those two staying the same. And it's important in the current, whichever way you solve for the initial current, I did it from left to right, is to draw the current in the same way. The polarity stays the same on the way you solve for the VC, okay? So polarities are determined by what you use to solve the initial with. And so this is the one where I get my initial value. Okay? So solving this to find VC of 0, you guys know I like node voltage, so I'm going to label this top one all the same. And I'm just going to call it VC because there's no current here, correct? So my equation is minus 4 milli plus VC over 0.1 plus VC over 0.1 and then 0 for that other, so that's my equation. Combining those, I get 2 over 0.1 and 4 milli, and then this becomes 4 milli times 0.1 over 2 to give me, sorry, 0.4, what is it, 0.2 milli, 0.2 millivolts. So this is my 0 minus value, and then I need to find the IL of 0 minus. So that's going to be the current going through this branch. Because that goes 0 to the right, that's all the same current, right? All this current just flows around through there because this is 0. If I know this node, I can find that current just by VC over 0.1, which gives me 2 milliamps. You guys see that? Okay. So now I know that this value is 2 milliamps. This value is 0.2 millivolts. So what is my current now here? I hear you guys saying it, 2 milliamps, right? Because this becomes an open, all the current in that branch is forced by the current source, so that's all just 2 milliamps. And this is my initial value for IC of 0. And then VC of 0 will stay the same, so that's 0.2 millivolts. Was there, I think I saw a hand. Did you have a question? Oh, okay. I thought I saw a hand. Okay, so those are our initial values for IC of 0 and VC of 0. Then we need to know the final value. For the final value, the switch is open. Inductor sat there for a long time, so that becomes a wire, and then the voltage is open, or capacitor is open. So now I need to know the voltage here, VC. Again, this is 0. It's a floating wire. So this is all the same node, and this is all the same node. What do you notice?
What makes the current flow through is that 0.01 ohm resistor on the far left.
Okay. So what is that, you said?
Seconds?
What value is this current?
What I found was,
Sorry, completely zoned out. Sorry.
No worries. Again, I don't see it, obviously, and so I'm going to go back to node voltage. So if all the top node is the same, then my equation will be minus 4 milli, and then I'm just going to call this VC again. VC over 0.1. There's no current here, and there's no current there, so that equals 0. So here I can solve to give me 0.4 millivolts. And that's my end value. If I notice that that VC is in parallel with those two other branches, and I know the current, 4 milli, it has to all go through the 0.1, I can use Ohm's law there too. So whichever way, if you see that, great. If not, just go back to node voltage and say, well, my top node I'm labeling, in this case I labeled it VC because it was easy to see, but if not, you could call it VX. And then you have to note like, well, VX is on top and then on the negative side, or I could ground that. Yes?
This is VC 0 plus, right?
This is final.
Okay.
So this is VC infinity of 0.4 millivolts. Okay? All right, the other two values I need to find is S1 and S2. And I forgot to write down your alpha and omega naught. I skipped over. So alpha first series is RTH over 2L, and RTH was 0.62, and L was 0.05, I think. Yep, 0.05. So this gives me a value of alpha was 6.2, and what's the units?
Meters per second.
Thank you. Meters per second. And omega naught is the square root of 1 over LC. And so 0.05 and C is 1 over 1.8. So omega naught ends up being 6. And what's the units for this one? Radians per second, great. And then, yes, I see that alpha is greater than omega naught, so this is where the overdamped. And then S1 is, copy that down here. So S1 is a minus alpha, and alpha was 6.2, so minus 6.2 plus square root of 6.2 squared minus 6 squared, and that gives a minus 4.64. And S2 is the minus 6.2 minus square root of 6.2 squared minus 6 squared to give me a minus 7.76. So I use both of these two numbers, and then I can plug them into the equation for A1 and A2. IC0 was 2 milli. C is 1 over C is 1.8. S2 was, what was S2? Minus 7.76. VC0 is 0.2 milli, and VC infinity was 0.4 milli. And then S1 was a minus 4.64, and S2 is a minus 7.76. So this gives me an A1 of 0.66 millivolts. And then again, replacing these, 1.8, 2 milli, minus 4.64. And then minus 7.76 minus a minus 4.64. And A2 is a minus 0.86 millivolts. So my VC of T ends up looking like 0.66 millivolts, E to the minus 4.64 T plus A2, which is a minus 0.86 milli, E to the S2, sorry, what was S2? Minus 7.76 T plus VC of infinity, which was 0.4 milli. And then the whole thing is multiplied by UT, and then the units is volts. So this would be my end equation for VC of T. And then, oh, I have another one, sorry. How do we find IC of T from this? Yes, we need to take the derivative. So VC of T dt. So if we take the derivative of VC of T with respect to T, the first one becomes 0.66 milli, and then the minus 4.64 comes down, e to the minus 4.64 T, and then a minus 0.86 milli times minus 7.76 e to the minus 7.76 T. And then the 0.4 milli goes to 0. And then we multiply by C, which was 1 over 1.8. And so IC of T will equal a minus 1.7 e to the minus 4.64 T plus 3.7 e to the minus 7.76 T. And this will be in milli and then times U of t amps. That will be your final answer. Okay, questions? Did you guys get very far? Okay. All right, so if you didn't quite finish this here, make sure to do as an exercise to be able to finish this and get the same answer, okay? Oh yeah, sorry. Or did I not? Oh, I don't have the plot here. Let's see. Okay. So this plotted, paste image, looks like this. So it will spike up to 2, and then it decays down, and then it goes a little bit below. You can see how it goes a little bit below 0, and then settles out at 0.
How does it go below 0? Okay. Right, yeah.
Okay. All right, any other questions? All right, see you guys on Wednesday, and we'll work on some more problems. Good question.
Sometime in February.
I thought it was like the first week.
Just because there's so many places making.
It will be February 7th.
You should just make it all RL and RC, strictly. No RLC.
But these might be useful, especially once we get into like
Is it just
and all that.
What is
Sure.
chapter 5?
I use them as much as you do, but I.
Yeah, so chapter 5 has the RL and the RC in it, and then chapter 6 is your RLC. So that you guys know all the content, it's just practicing all these types of problems. So you'll want to practice all the different conditions.
I had a couple questions about the lab.
Yeah.
I should have reviewed it more in fully before the first lab last week. But I was wondering, is there no lab 1A?
Sorry, just 1 second. Okay, if it is overdamped. Okay. Okay, I think they're all good. All right, see you guys.